Now we're going to look at the common emitter phase inversion. As discussed before, the output voltage at the collector is 180 degrees out of phase with the input voltage at the base. Therefore, the common emitter amplifier is characterized by a phase inversion between the input and the output. This inversion is sometimes indicated by a negative voltage gain. Okay, so you just have a minus AV. The DC input resistance, Rn, viewed from the base of the transistor was given in a previous equation. The input resistance seen by the signal at the base is derived in a similar manner when the emitter resistor is bypassed to the ground. So they go through the mathematical iterations here. Rn being VB over IB, VB being IE/RE, that internal resistance to the transistor. I sub E, the emitter current, then is approximately equal to beta AC IB, and Rn is approximately equal then to beta AC base current internal resistance divided by base current. The base current terms then cancel, and we're left with Rn approximately equal to beta AC RE. If the emitter resistor R sub E is not bypassed, the emitter resistance must be added to the R sub E first. Total input resistance for a common emitter amplifier. If we view the amplifier from the base, Rn is the AC resistance. The actual resistance seen by the source includes that of the bias resistors. We'll now develop an expression for the total input resistance. The concept of AC ground was mentioned earlier when we did the common emitter with the bypass capacitor. At this point, it needs some additional explanation because it's important in the development of the formula for total input resistance, Rn total. Okay, so another formula to add to your notebook. You've already seen that the bypass capacitor effectively makes the emitter appear as a ground to the AC signal because the reactance of the capacitor is nearly zero at the signal frequency. Okay, going back to our basics of reactance. Of course, to a DC signal, the capacitor looks like an open. Again, back to the fundamentals. Thus, it does not affect the DC emitter voltage. In addition to seeing ground through the bypass capacitor, the signal also sees ground through the DC supply voltage source VCC. It does so because there is zero signal voltage at the VCC terminal. Thus, positive VCC terminal effectively acts as an AC ground. As the result, the two bias resistors R1 and R2 in the voltage divider appear in parallel to the AC input because one end of R2 goes to the actual ground and one end of R1 goes to the AC ground, the VCC terminal. Also, Rn at the base appears in parallel with R1 and R2. This situation is illustrated then in the diagrams in 1720. The collector resistor R sub C does not affect the input resistance because the collector base junction is reverse biased. So they've taken this via the explanation here of what's going on with the grounding of the resistors. This is what we end up with, the parallel equivalent R1 and R2. The expression for the total input resistance for the common emitter amplifier as seen by the AC source then is that Rn total is equal to R1 in parallel with R2 in parallel with Rn. The collector resistor has no effect because of the reverse bias base collector junction. If we look at collector or current gain for the common emitter, the signal current gain for a common emitter amplifier then is AI. So now notice we've changed the subscript now from voltage gain to current gain is the collector current by the um, uh, source current. Okay, so I sub C, I sub S. You got to keep these things straight. Where I sub S is the source current and is calculated by VN RN total. The power gain then of a common emitter amplifier is the product of the voltage gain and the current gain. Okay, so we take our voltage gain, A sub V, we take our current gain, A sub I, we get A sub P. So in an example here, determine the voltage gain, current gain, and power gain for a common emitter amplifier in the diagram. They're saying let beta DC and beta AC both equal 100. Express the voltage and power gains in decibels. So there's our circuit. So first we need to find the internal resistance, R sub E. To do so, we must find the emitter current. Begin by calculating the base voltage. Okay, so we're going to find the base voltage. So the base voltage then, that's our what? That's our divider, our voltage divider again. So R1, R2, VCC gives us 2.73 volts. Now we can calculate the emitter current. The emitter current is the voltage across the emitter by that resistor R sub E. So we're right here in the diagram. So V sub E then is equal to the base voltage drop minus the barrier voltage, 7/10, divided by the emitter resistor. So we're dealing with just this area here. So 2.03 divided by 1K gives us 2.03 milliamps. Now we can determine the internal resistance for the emitter. So there's that formula they told us, just accept it. 25 millivolts divided by the emitter current. 25 millivolts by 2.03 milliamps gives us 12.3 ohms. So, sorry, there are a lot of calculations here, but you need to keep track of them. The AC voltage gain then is A sub V, approximately equal to RC by RE, the internal resistance. So 4.7K divided by 12.3 gives us a value of merit, figure of merit, 382. Determine the signal current gain by first finding Rn total to get the source current. So Rn total then is equal to R1, R2, and beta AC by the internal resistance gives us 100K, 10K, and 1.23 K ohms. So you do our math for resistors in parallel, we get 1.08. Remember the rule? Smaller than the smallest, 1.23, 1.08. The source current then, Vn over Rn total then, 100 millivolts divided by 1.08 kvolts gives us 9.26 microamps. So now we can determine I sub C, the collector current. The collector current then is equal to the output voltage by the collector resistor. So output voltage is, by definition, V in by V out is AV. So V out is AV by V in divided by R sub C gives us 813 microamps. AI, the current gain then, IC by I source, 87.8, again, unitless. The power gain then is A sub P, AVAI gives us 33 by 540. Okay, so 33,540. The voltage gain and the power gain in decibels then, so we take that 382, 20 times the log of that gives us 51.6 dB. For the power gain, we're at 10 times the log. Remember, power is not 20, power is at 10. 10 times the log of 33,540 gives us 45.3 decibel. So when we come back, we switch gears now from the common emitter to the common collector amplifier.